Thanks a lot. So after the lectures, after my last lecture, I realized that I still have material for like 4 or 5 hours. So what could I do? Either hide somewhere or run away, but then I would miss the nice excursion tomorrow and maybe even the conference dinner. So I decided I would cut down to the things that I think are the most essential ones today. And I still provide all my material on the web page. You will find more slides than I ever used here, but you can read them through, for instance. First, a remark. You all got an email via Anna about the data that you can download and the links that I provide in the slides, but the links didn't survive the generation of PDF from PowerPoint, and then in the mail there is a line break missing. You will see, probably find that you can spot it. It's before X and Y are defined. So there's I don't quite remember the line that it is, but it's like 2 lines concatenated where there should be a line break before the capital X. Mm-hmm. Yeah, otherwise you just get an error message and you don't download anything. Okay, so what I want to talk today about is, in the first part, my favorite framework for classification, which is distance-based and prototype-based classification. So you have seen in Dalia's lectures and a little bit in mine also, prototype-based systems for unsupervised learning. And I will now talk about supervised learning with prototype-based systems. So this is, in a sense, a completely different philosophy from the support vector machine. As I said yesterday, the support vector machine focuses on the difficult example in your data set, those that end up close to the boundary between the classes. Right? These are called the support vectors. In prototype-based learning, you try to emphasize the role of the typical examples of the classes, as we will see here. So it's a different philosophy from which we start, and of course we get different classifiers with different properties. So I will not discuss k-means and vector quantization anymore because I already did that. I will then take you from a classical classifier, which is the k-nearest neighbor classifier, and almost anybody should know that, to learning vector quantization, which is my favorite working horse in classification. And I will also discuss the role of distance measures and relevance learning, which is adaptive distance measures, which is an interesting concept. Okay, so I will do that and that. Here we go. So the KNN, or nearest neighbor, or k-nearest neighbor classifier is about the simplest classification that you can do. You have a data set, say here 2-dimensional data points in this illustration. You know which classes they belong to. You simply store all the data that you've ever seen, and you use this as a reference base for classification. How can you do that? Well, you get a new data point that you want to classify, and now you need something that you can use as a similarity measure. You need something that allows you to compare this data point with all the data points in your database that you have stored. So for instance, if it's 2-dimensional vectors or n-dimensional vectors, then a natural choice or very intuitive choice is Euclidean distance. We will discuss whether that makes sense in general, but this is at least an idea. So I can here simply measure the distance of this gray point from all the points in my data set, and then I would say, oh, the closest, the nearest neighbor in my data set is a green data point, so I would also assign this data point to the class of the green data points. And locally, this means I introduce a little decision boundary here, which has the same distance from the green and the blue. Right? And anything above this line here, this short line, would be assigned to the green class. Anything below would be assigned to the blue class. Now, if you take that for serious, you can go through, you could, in principle, go through your data set, and in 2 dimensions you can do that, of course, and draw the decision boundary between the 2 classes anywhere in your space here, in your feature space. So this would be a piecewise linear decision boundary if I use Euclidean distance, right? Now this is the nearest neighbor classifier. You can generalize that by looking at k nearest neighbors. So for the gray point, I determine, I don't know, the 5 nearest neighbors in my data set, and then I let them decide by majority vote which class I want to be, this point should belong to. So this is conceptually simple, right? It doesn't get any simpler in classification. This is easy to do. You don't even have to do any training, any machine learning in the strict sense, because you simply store the data and then you compare any new data point with your reference points. And there's essentially only one parameter, which is the k in the k nearest neighbors. How many neighbors do you want to use? There is, of course, a hidden kind of parameter or concept in that you have to choose a distance measure that you use for the comparison, right? Okay. The downsides of this can get very expensive. You might have to store a lot of high-dimensional data, so storage might be expensive, and computation gets expensive. If you get a new data point, a query that you want to assign to one of the classes, in principle you have to compute all the distances to all the points in your data set, and then find the largest one. So you also have to do a sorting, and that can get expensive. You also see here in this cartoon, which is just a made-up illustration, that you are very sensitive, your classifier will be very sensitive to single examples. Like this blue one here, this thing here is labeled blue, and that will define, in the nearest neighbor classifier, a little island, and all data points that fall into this region here will be assigned to the blue class. But we probably wouldn't even believe that. We would believe in more smooth boundaries between the classes, so maybe this is just mislabeled, but we're taking it too serious, right? So we would be sensitive to mislabeled data, for instance, and in general we get a very complex decision boundary between the classes, very wiggly thing. Now, this is exactly the point where Kohonen entered the scene and said, okay, let's improve this and get better, smoother decision boundaries by replacing our full data set. Instead of using all the individual data points, come up with prototypes that represent the data, the typical properties of the data. So we would have a red prototype, a green prototype, a blue prototype, and maybe yet another blue prototype. You're free to define the number of prototypes you want to use. And now this data point would be assigned to a class by comparing the distances to all the prototypes rather than to all the data points. So here we would say this is closer to the green prototype than it is to the blue prototype, so we will still assign it to the green class. And here we have a local decision boundary between these two prototypes. Here we have a local decision boundary between these two prototypes, and here we have a local decision boundary between these two. But these are much simpler, obviously, than the one that the k nearest neighbor classifier gives you. In fact, once you have identified the prototypes, you can forget about the individual data points, because you use them to come up with the prototypes. So again, we have local linear decision boundaries if we use Euclidean distance, but they become more smooth, they become more robust. The single blue point doesn't have as much as an influence as it had in the previous case, because it might determine to a little extent where we place our prototypes, but it's not taken serious as a single data point as much as it was before. Right? So this is much more robust. I have low storage needs. In the end, I only need to store my prototypes, not all the data anymore. I have very little computational effort because, like in this illustration, I would have to compute only 4 distances rather than 50. And if my data set is very large, this saves a lot of computation. And this is a natural tool also for multi-class problems, like the problem that we have with the SVM, as we discussed it yesterday in the questions, at least, is that it's a binary classifier. Well, this type here is a multi-class classifier by definition. You just need at least one prototype per class that you want to consider. That's a natural tool for multi-class classification. Some more advantages. I end up with a classifier which is parameterized in the feature space. The prototypes are comparable to the feature vectors. Right? So if your data is medical data, blood pressure profiles over 24 hours, your prototypes will also be interpretable as blood pressure profiles over 24 hours. So you have immediately insight in what is happening. You can go to the domain expert, show him or her the prototype, and discuss things with him, which is, or her, which is very difficult with the weight vector of the support vector machine or even with a multi-layer network to discuss the outcome of the training process in terms of the actual classifier. Here it's very easy. The downsides, as in any machine learning, is that we have to do some model selection to some degree. So we have to decide how many prototypes we want to use per class. That's difficult to find out and justify, and requires validation procedures. And of course, as opposed to the KNN, to the nearest neighbor classifier, we have to do some training here. How do we place the prototypes given our data? Okay, so here's the mathematical formalism. This is almost the same as for the vector quantization in the beginning. We have a set of prototypes, but now these prototypes carry labels. They represent a class, right? Each prototype has a label, and we will end up using this as a nearest prototype classifier, meaning that we compute for any possible input vector, we compute the distance from the prototypes, we determine the prototype which is closest to the data point, and we assign the data point to that prototype, as in vector quantization, but now it's learning vector quantization, so it's supervised. So we also say the data point is of the same class as is given by the label of the prototype, right? Okay. Now this requires essentially that we have a meaningful distance measure, which doesn't necessarily have to be a metric. It should have the property that the distance of a point to itself is 0. That's a natural condition. And it should be non-negative, at least, if the two arguments are different. That's the minimum requirement that we need here. Otherwise, it doesn't make sense. The most prominent example, of course, is Euclidean distance, which is a metric and fulfills all these properties automatically. Great. The big question is now, how do we place the prototypes? And Kohonen already gave the answer. The first algorithm that was suggested is called LVQ1, because it's the first suggested by Kohonen, and it works like this. We initialize prototypes for different classes somewhere in our feature space. So in the illustration, it's two-dimensional, obviously. We present a single example from our data set, and that is labeled as a blue data in this case. We determine the closest prototype among all prototypes that we have. Currently closest prototype, this is the winner. Now this is a blue prototype, so it's supposed to represent blue data. We move it where we observe a lot of blue data. So in this case, we would move it even closer to the observed data point. We move on. Next data point from our set sits here in the feature space, is labeled as a green example. Belongs to the green class. We determine the closest prototype, but this is now a red prototype, so it's not supposed to represent green data, right? So what do? We push it away from the observation. And the hope is, and this is pretty intuitive, that in the end we have prototypes placed in regions of feature space where there was predominantly data from that class, right? So we would come up with a piecewise linear approximation of the density of classes in feature space. There you go. And any new data point now, no, this is not here, any new data point here will be assigned to the nearest prototype according to these regions here, which are sometimes called the receptive fields of the prototypes. Okay. So that's pretty easy, pretty intuitive thing to do. Mathematically, what I just told you is the following. We randomize initial positions of the prototypes, and you don't do that stupidly. You go, for instance, to the class conditional means. So you take all the blue data in your set, you take the mean vector, and you put your prototype initially there. That's a clever initialization. Then you present data sequentially, so input vectors and labels. You determine for a single example the winner, and then those who remember ABBA, the winner takes it all. In this, you determine the winner, and you updated it by moving it closer to the data point or pushing it away from the data point. And mathematically, this means you move it along this axis, and the prefactor is positive +1 if the label of the data point and the prototype is the same, and it's -1 else. And as in almost all machine learning algorithms, you have here a learning rate, which is like the step size of your update. How much do you move the prototype? Now, there are many heuristic variants and modifications. You can play with the learning rate. You can come up with time-dependent learning rates. You can update more than one prototype per step, not just the winner, but also the second, and other schemes exist. But the basic idea remains the same, and all the variants that you will find in the literature go back to LVQ1 philosophically in the basic ingredients. So here it is again, LBQ1 update step, as I just explained it. Now, if you take this series, you can write it here as a derivative of Euclidean distance with respect to the prototype, to the winning prototype, right? W minus x squared, taking the derivative, would give you this term. So you can rewrite this as a derivative of Euclidean distance between the winning prototype and the data point. And this then looks like the instantaneous gradient taking with respect to the prototype of that distance. Why do I tell you that? Because it means immediately, if I go for a different distance, I can construct my LBQ algorithm by inserting here something else than Euclidean distance. All it needs to satisfy is a condition that it's differentiable with respect to the prototype. And then if you come up with your own personal favorite distance measure for your problem, you can construct your LBQ1-like algorithm immediately, right? And the update works always like that the distance, whatever it is increased if the data point and the prototype are from different classes, and it's decreased if the data point and the prototype are from the same class. Okay. Euclidean is the most intuitive, but you can use any other differentiable distance measure here. You can go even further. You can do cost function-based learning, where you say, I define an overall cost function, which is a sum over all examples in my data set, right? And the contribution of a single example is, for instance, this thing. This is the most famous example, which is called generalized learning vector quantization, GLVQ, which was suggested in the 90s. And what you have here is the distance of the data point that you're considering in the training from the closest prototype that carries the same label, and the distance of the data point from the closest prototype that carries a different label. So WJ is the closest correct prototype from the same class. WK is the closest wrong prototype from any other class. And of course, you want this to be, you want to be smaller than that. You want your data to be close to a correct prototype and far away from a wrong prototype. So you want to minimize what is upstairs. Downstairs, we only have a normalization. It's the sum of the two distances. And then maybe I can use a squashing function here, a transfer function in addition. Basically, what I do here is I favor a small number of misclassification. If you think of phi being something like a sigmoidal function, then it means we favor small values, negative values preferred, of this argument here, and we punish large values, positive values of this argument. Now, a negative value indicates that the data point is already classified correctly. It means that the distance from the correct prototype is smaller than the distance from the wrong prototype, so the winner, the absolute winner, will be the correct prototype. If this argument is positive, we have a misclassification. And if you consider this as an approximation to a step function, then this simply counts the number of misclassifications. So it makes sense to reduce this, to make this as small as possible. Also, we want to have a large difference between the two. So this has the spirit of a large margin classifier. We want the difference between the distance from the correct and the wrong prototype to be very large, right? And this will place prototypes in positions in feature space where they represent the class as well. So we can hope for having class-typical prototypes in the end. Right? Now, what is the training process? Optimization with respect to the prototype position of this cost function. And you can do that with whatever method you want to use. For instance, you can do stochastic gradient descent, similar to the neural network idea. You present single examples. At each time step, at each example, you determine the prototype which is the closest and correct, and the prototype which is the closest and wrong. And then you update both these two prototypes, the correct winner and the wrong winner, according to a little gradient step with respect to the cost function contribution of that example. So the sum of all the examples would be the full cost function, but you look at only one example, so you take the gradient of only this contribution of the data point that you're just looking at. In the slides, in the PDF, on the next slide, you would see the full form of this. I spare you that today. I only tell you that, well, you get some prefactor from working out the derivatives of the cost function terms, and in a sense, this looks like LBQ1 always, or almost, because what you do is a correct prototype, the correct winner will be moved closer to the data point. The wrong winner, the incorrect winner, will be moved away from the data point. So you're doing almost the same as an LBQ1, only you apply it to 2 prototypes at a time, and you have a more complicated prefactor which is worked out on the slides. But I don't want to confuse you with the precise form. See the PDF handout for that. Okay. Now, how can we use that? As I said, we can use Euclidean distance. We can optimize the prototype positions going through our data set again and again until they converge to some point, and then we have a nearest prototype classifier using Euclidean distance. But I already told you we can also use other distance measures, right? So normally, or very often, people predefine their favorite distance measure, or they have some insight into the problem, and they know Euclidean distance doesn't make sense, we should use Manhattan distance or some other distance measure. And then you can construct your LBQ1 or your GLBQ based on this distance measure. So for instance, instead of plain Euclidean, you could go for any Minkowski measure, which looks like this, and construct your LBQ scheme, right? And then you place prototypes according to this distance. And of course, you should also use this distance then later in the classification scheme to be consistent, right? So a possible workflow could be, well, let's try several distance measures if I'm not sure which is a good one for the problem at hand. And then compare the performance in the sense of cross-validation for various choices that I can make and pick the best one in the end. Examples besides the Minkowski measures would be kernelized distances or divergences in statistics. If your data, for instance, if you're looking at images but you don't classify the images directly, you take some color histogram over the image, then your data feature vectors become histograms. And you can compare histograms in terms of entropic distances, relative entropy, or divergences as they are called in statistics very often. Famous example, Kullback-Leibler divergence. Compares 2 densities or 2 histograms and gives you a distance measure, which is very abstract compared to Euclidean distance, but it's differentiable normally, and you can use it in an LBQ scheme, right? What is a kernelized distance? Well, I talked about kernels in the context of the S3M, and in principle, you can write any distance, like the Euclidean distance, obviously. You can also write it relating it to a dot product. So if you work out the squared Euclidean distance between the input vector x and the prototype y, then this is it, right? And here we have the dot product as part of that. If I have a more abstract distance, where I know that dot products can be represented by a kernel function, very much as in the SVM, then I can associate a kernelized distance with that by just taking the kernel of WW minus 2, the kernel of WX, and add the kernel of XX, which is the equivalent or the analogon of the Euclidean case, now for a more general dot product, which is represented by the kernel. So you could use a kernel as the Gaussian kernel, define your kernelized distance according to this line here, and use that also in LBQ. And the purpose would be, of course, to make things more separable that are less separable in the original feature space. So you can extend LBQ even to kernels, right? If you want to learn more about distance measures in general, I cite here 2 of our review papers about that, and I will, after the school, I will provide you with some sort of syllabus with many references and stuff, but I didn't manage to finish that beforehand. Okay. Now the question is, of course, what is the right distance to use for the problem at hand? And if we take the wrong distance, this can have strong influence on the quality of the result. If we, well, talking to astronomers, if you look at the stars and you define as distance between stars the angle at which you see the star, rather than the 3-dimensional Euclidean physical distance, right? Which is the same as saying you normalize all your stars to a unit sphere around the Earth, right? That's what you see. Then you end up with astrology rather than astronomy. Because you would say, oh, look, there's an interesting structure here. These form something that looks like an animal, or in this case, like a Big Dipper. And this cannot be by chance. This must mean something. But it's nonsense, because these stars are not close at all. They can be very far away in the 3rd dimension, but we've projected them to a sphere, And then astrology starts by over-interpreting this and seeing little animals or other creatures or a Big Dipper in that case. It gets even worse if you combine that with overfitting. If you over-interpret your data, instead of the Big Dipper, you get, for instance, the enormous kitchen, because you assign every little detail to some meaning, which is total nonsense, right? And all that because you're using a wrong distance measure and you're over-interpreting your data. Okay. So we have to be careful about using exotic distance measures or different distance measures, and we have to check whether this really makes sense, what we are doing. There's a very elegant approach to choosing a distance measure, which is called relevance learning. And this sounds like a strange idea at first. Instead of using a fixed distance measure, let us only fix the mathematical form of the distance measure. Let's parameterize a distance measure, and then this means this distance measure has parameters that we can play with. And we can tune the parameters in the training process. So we will not only push around the prototypes, at the same time we will change the definition of the distance in the learning process. Sounds a bit weird, but it's an attractive concept and we will see it works. So we define only the form of the distance, we optimize its parameters in the training process in the same data-driven training process as we move the prototypes around. So it's not a pre-processing step and then training of the prototypes, it's one unified approach. And the example I want to discuss is matrix relevance learning vector quantization, names get longer, which is a data-driven optimization of prototypes and a distance which is defined by a relevance matrix. I will show you what that is. So as I said, this is not pre-processing and then training, it's done in one go. Here's the distance measure. It's just one step away from Euclidean distance, right? Instead of taking w minus x squared, I take w minus x transpose, then I insert a matrix lambda here, and then I multiply with w minus x. So if this matrix is the identity, we're back at the squared Euclidean distance. But now I have a matrix of parameters that I can play with, right? Okay, minimum requirement for a distance was it should be non-negative. So lambda should be a positive semi-definite matrix at the very least. How do we make a matrix positive semi-definite? Easy. We reparameterize this as the square of another matrix. So we write lambda as omega transposed omega, and omega could be another n by n matrix. So this is an n by n matrix because both the prototypes and the data points are n-dimensional vectors. Right? Now we have guaranteed that this is non-negative, that's fine, and instead of choosing lambda explicitly, we simply choose the parameters, the elements of omega, which then defines lambda, and that defines the distance measure. But there's also another interpretation now, because if I rewrite that, you see that this is omega times w minus x squared. You get exactly that. So we can interpret omega as a linear transformation of all prototypes and feature vectors, and in that transformed space, we use plane Euclidean distance, or plane quadratic Euclidean distance. That's two interpretations, which is the same thing. But omega is the adaptive thing here. That we can change in the training process. So either we say we train a different distance measure, we obtain a different distance measure from the training, or we say we train a linear transformation so we can use Euclidean distance in that transformed space. But mathematically, it's the same thing. So training then is the adaptation of the prototype vectors, but also the elements of omega. And how can we do that? Well, it's easy. This is a distance measure which is differentiable. We can use it in the GLVQ cost function that I just showed you, and do gradient descent with respect to the prototypes. That's plain vanilla GLVQ. But we can add on top gradient descent with respect to the omega contribution, to the omega elements. It's a cost function now of the prototypes and the matrix omega, and we can optimize, minimize the cost function with respect to all the degrees of freedom that we have. Bingo. There we have a training process for matrix relevance learning, vector quantization. Because it uses the GLVQ cost function, it's then called generalized matrix relevance learning vector quantization, GMLVQ. I stop here with even longer abbreviations. Now we can play with this. we can, instead of using one matrix lambda for the entire feature space, we can use different lambdas for different classes, different lambdas for different prototypes even, which we would end up with localized GMLVQ, right? Or we can make things simpler and say, let's make lambda a diagonal matrix rather than a full matrix. That corresponds to assigning to each feature dimension one weight rather than a full matrix to the whole system, right? We can even use rectangular matrices omega. Nobody says that omega has to be n by n. All that we have to guarantee is that lambda is n by n. So if you have 1,000-dimensional feature vectors, you don't want to use really a 1,000 by 1,000 relevance matrix. That could get expensive, right? But you can use a 1,000 by 10 matrix omega, right, which then produces a low-rank lambda. And intrinsically, in this space here, you use a low-dimensional representation of the data. So you can play with this a lot. I will stick with the basic variant where we use one global lambda, which is n by n. Okay. Now, after training this system, for instance, by gradient descent-based techniques using the GLVQ cost function, we get prototypes which represent typical class properties, hopefully, or subtypes of classes if I have many prototypes in one class. The relevance matrix I can also interpret, and that's very attractive because lambda ij, the element of the relevance matrix, quantifies the contribution of the pair of features I and j to the distance measure. The distance measure is a quadratic form. Lambda ij is the coefficient of the contribution that comes from feature I and feature j in the prototypes and in the data. And in particular, the diagonal elements of lambda jj summarize the contribution of a single feature j to the distance. So they add up the contribution that feature j has in the construction of feature I in the transformed space, and I add up all these, that gives me lambda jj. So intuitively, lambda jj measures how important feature j is for the distance measure, and that means how important it is for the classification. And that's why we call it the relevance of the feature, right? Now, this interpretation saying that large lambda jj means the feature is important and small lambda jj means it's not important implicitly relies on the idea that the original features all have the same magnitude, right? If you have a feature that ranges from minus 1,000 to plus 1,000 and another feature that ranges from minus 0.1 to plus 0.1, then you cannot immediately interpret the prefactors as relevance, right? Because you have to compensate for that scaling. But if we z-score transform all our data so that the per feature I get a zero mean over the data set and a unit variance over the data set, then we have something which is interpretable in the sense that large lambda jj really mean importance, relevance of that feature. Okay. The most frequent question I get at this point, probably not today because we're all tired from the lovely conference dinner, is, well, this is just Mahalanobis distance. What's new? No, it's not Mahalanobis distance. Mahalanobis distance uses the covariance matrix of the feature vectors that we have in our data set, and it's fixed. It's not adaptive, not at all. You compute it once and forever, and you can use it as a meaningful distance, but it's not the relevance matrix in the system. So it's a generalized Mahalanobis distance. That's the next point. Yes, if you insist, it's a generalized Mahalanobis distance, and this is a generalized broccoli, and this is a generalization of Ohm's law. It has the same mathematical structure, but that doesn't mean it's a generalized Mahalanobis distance. That statement doesn't make any sense. Okay. How do I train? Well, I optimize prototypes and distance measure according to the gradient of the cost function with respect to the prototypes and with respect to the matrix omega, the elements of the matrix omega. And you can work that out, and you get a clean stochastic gradient descent-based optimization that gives you a good solution, and here's the full form, don't look at it, which means as much as look at it. But don't try to remember this at all. Okay. So we optimize prototypes and the distance measure in the same training process. The motivation is, of course, to get improved performance. The weighting of the features and the pairs of features should give us better performance of the classifier. That's the hope. We also can hope for simplified classification schemes. Why that? because maybe some of the lambda jj become very small or 0. What does that tell us? Well, the classifier doesn't use that feature for the classification at all. It doesn't contribute to the distance measure. So we don't have to measure it at all. We can forget about it right away. We can come up with a simpler classification by omitting these non-informative features. Perhaps it's just noise, right? Then forget about that. We also can get a discriminative low-dimensional representation. I will show you an example of the data. We can obtain insight into the data. We can find which are the most important features in your data set that determine the class memberships. We can also try to incorporate prior knowledge by imposing some special structure on omega if we already have an idea about the interplay of the different features. Okay, here's an example. This is the famous iris flower data set that goes back to the 1930s by Fisher, where I applied GMLVQ, the generalized matrix relevance learning vector quantization, to that data set. It's a set of four-dimensional feature vectors. These are the prototypes for the 3 species of iris flowers that are in that data set. And you see, so this we can interpret as representatives of the classes. And this is the relevance matrix in terms of the diagonal elements. And this tells me feature 1 and feature 2 are apparently very unimportant for the classification. It's 3 and 4 that is most important. And this is the interplay. I can read off here how important is a pair of features in the distance measure. Okay. A nice property of the relevance matrix is that it becomes low rank in the training. We have observed that empirically. We have, in the meantime, shown it mathematically that this tendency exists. So in the end, the relevance matrix is dominated by just a few eigenvectors. And that means it prevents overfitting, naturally, because you could have the idea that if you introduce this n by n matrix in a 100-dimensional space, that gives you roughly 10,000 more parameters than you had before, and that should be prone to overfitting. But really, the matrix becomes low rank. There's only a couple or one leading eigenvector that dominates the matrix, and that means you have a number, effectively a number of degrees of freedom which is linear in n, not n squared. And that prevents overfitting, but it also helps you as you can come up with a discriminative visualization of the data. So here's the iris flower data set with the 3 classes, the 3 species, projected on the first eigenvector of the relevance matrix and projected on the second eigenvector of the relevance matrix. So this smells like PCA, but it's not, because it's supervised learning, right? And I use the relevance matrix, not just the correlation matrix, covariance matrix. And you get here a visual impression of the data set that tells you, well, that the green and the red species of iris flowers are closer together and that the blue one is pretty much separate from the 2 classes. So you get an insight into the problem, into the class, into the data. Here's a multi-class example which has 6 classes. This is about coffee, that's why it's important. These are 6 different kinds of coffee, brands of species of coffee beans. And what they measure in Magdeburg is a near-infrared spectrum of the coffee sample. And this is the feature vector. So this is represented as 256-dimensional feature vectors. I did GMLVQ on that, and you get a similar visualization of the data set where you see that the classes, some classes separate well, some don't, some overlap a lot. So you get an insight into the structure of the problem. This is galaxy classification. It relates to the poster that Arike is presenting here. Here we have the same visualization for 5 different classes of galaxies based on 40-dimensional feature vectors derived from images somewhere, but we don't use the images, we use the features. And you see, for instance, that class 2 and 3 overlap more than the others and so forth. If you look at the relevance matrix, the diagonal of the relevance matrix, then we see here that some stick out. These seem to be important. Some features seem to be important. And the red arrows here indicate which the domain experts, astronomers in that case, in a previous paper had hand-selected as important features. And you see that some of them are not at all important, apparently, at least not in the context of GMLVQ. So it gives you additional insight into the problem. Okay. Related schemes. GMLVQ is not alone, of course. There are many schemes that do similar things. LDA, linear discriminant analysis, has a similar structure, yet it's very different. It's a different objective function, and the matrices that appear there go back to essentially the Gaussian mixture idea, and they're not adaptive as in the same way as the relevance matrix are. Relevance learning schemes appear also in other supervised learning, in radial basis function networks. And there's neighborhood component analysis. There's large margin nearest neighbor by Kilian Weinberger, who suggested a very similar idea, an adaptive distance measure in a nearest neighbor classifier, which is very attractive. And if you Google that, you will find also downloadable code for using it. There are many variants of the relevance LVQ. I already discussed a few, but I don't have the time to go into details. If you want to use GMLVQ in MATLAB, there are two available toolboxes, one with all the bells and whistles prepared by Kerstin Bunte in Groningen, and one with only the basic versions prepared by myself. And don't look at the code, just use it, don't read it, it's ugly. I learned programming in Fortran. And some of you probably don't know that Fortran is a programming language and not a cheese or sausage or something. And then after a couple of unhappy years using C, MATLAB came along, and I switched to MATLAB, and that's where I am. And so this is my world. But there's also a Python version of the toolbox, which is scikit-learn compatible, and you can use it in the tutorials. It's also in the links. Okay. If you want to learn more about, ask me in person or visit my homepage. And there are also some references on the slides, but I don't have the time to go into that. So I hope I still have like a quarter of an hour or something. Yes. Yeah, that's brilliant. So this was prototype-based supervised learning, which is, I wouldn't call it exotic, but it's not as popular as other classifiers, but it has its merits. And in particular, it's a close relative to unsupervised prototype-based methods, and you can do both on the same data set, and that gives you additional insights and feelings about the problem and the data. And in particular, the relevance learning part I find very useful in practical problems. Okay. I had a whole set of slides about shallow neural networks and regression and gradient descent. I don't have the time to talk about that, but you will find them in the set. And Mark presented so much about neural networks that I don't think this has priority. I would like to end with some practical considerations. General remarks and practical considerations about supervised learning. First one is accuracy is not enough. What do I mean by that? Okay, say you have a data set, you train your favorite classifier, you do some validation, you get a test set performance of the classifiers after training, where classifier A gives you an overall accuracy of 75%. So 75% of the test examples, test data is correctly classified to one of the two classes. Classifier B gives you only 70% accuracy of classification. Which is the better classifier? A, huh? Clear. Well, if it's a two-class problem, maybe the situation is the following. Class 0 data is classified by A with 100% correctly. Class 1 data is always classified incorrectly. How can you get that? Well, classifier A simply says everything is class 0. Hooray. But maybe in your data set, there's just 75% of class 0 data, so you get 75% correct by being stupid, right? Classifier B worked hard to come up with something that classifies data from class 0 with 70% correctly, and data from class 1 also with 70% correctly. So we would have the feeling that classifier B has learned more from the data than this stupid classifier A. So B is the better classifier in that sense, right? Okay. The problem is that very often you have strongly biased classification tasks. So if you think of medical data, where you're looking for rare diseases, rare medical conditions, then of course we're very happy that this is a biased problem. Most people don't have a rare disease, and only a few have a rare disease, because otherwise it wouldn't be rare, right? You might also have the problem that the data you have at hand has a different bias than the real world data, right? So if you select some data set somewhere, it has a composition in terms of classes which could be totally different from the real world out there. You train on that data and you want to use it in the real world later, you will fail miserably, right? Also, it is important to note that the two types of error in a two-class classification problem can be very different in consequence. Again, think of medical diagnosis, and you mentioned that already. If I say somebody is healthy but he has the disease, that has totally different consequences from saying the patient has the disease but really he or she is healthy, right? Both can be catastrophic, but they are totally different in general in terms of the seriousness of the consequences, right? So what you really have to do is you look at the class-wise occurrences, so you come up with a confusion matrix of your problem, and in two class problems it's pretty simple. And you have here the number of true positives, the number of false positives, the number of false negatives, and the number of true negatives. And you define rates like the true positive rate, or the true negative rate, or the two other rates that you can define, and the false positive rate and the false negative rate. And these are the essential quantities that tell you a lot about your classifier, a lot more than just the overall accuracy. Now, these rates are not independent because they add up to 1, some of them, because they are probabilities. Many more quantities can be derived from the confusion matrix, and very often the same quantities go by very different names in different disciplines. So you have precision, you have recall, hit rate, sensitivity, specificity, positive predictive value, and what was it, what you said, pureness and?
Completeness and purity.
Completeness and, yeah, okay. Just the same thing, different name. So don't be surprised if you come across different names for these quantities. And then people have come up with performance measures which are based on these rates, the balanced accuracy, the F1 measure, the Matthews correlation coefficient, all in an attempt to boil down the performance of your classifier to one number that gives you some insight into its performance. My advice is don't even try to remember all these definitions. Look them up once you need them. Well, the receiver operating characteristics, that's the thing to do, at least in a two-class problem, that gives you the full information about the quality, or much more complete information about the quality of your classifier. So I want to go through that again. Many classifiers have some sort of discriminative function. It doesn't need to be a probability for class membership. It can be anything that changes continuously, and where we say if the value is below some threshold, we would like to assign the data point to class 0. If the value is above some threshold, we would assign it to class 1. Simple example, the perceptron. W dotted into X, if it's positive, we say it's class 1. If it's negative, we say it's class 0. And W dotted into X, the dot product, is then the discriminative function that can change continuously for every input that I consider. Now, let's introduce some bias. Instead of saying compare the discriminative function with 0, compare it with the parameter theta, which is the same as saying take your perceptron but introduce a local threshold here. And now I can consider the classifier for all possible values of theta, and I determine for each theta the true positive rate and the false positive rate, and then I plot the TPR versus the FPR, getting rid of the parameter theta. So if we set theta to infinity, all data will be assigned to class 0. Hooray, we have no false alarms, right? On the downside, no positives are detected whatsoever. No class 1 data will be detected at all. Okay, so let's set theta to minus infinity, then everything is assigned to class 1. I will find all positive cases, but I have the maximum number of false alarms. Now, the truth is in between. These are the two extreme points. Here I plot true positive rate versus false positive rate. For all thetas, I get a curve. For theta equals 0, I get the naked perceptron. That's just one working point that has a particular set of false positive rate and true positive rate. These are the two trivial cases. And by playing with theta, I can move along this curve, right? Now, this is corresponding to random guessing. So I want to be as far away as possible from random guessing. And I can measure that by computing the area under the curve, the AUC. And the larger that AUC, the better in general is my classifier, because the perfect one would have an AUC of 1. right? That's a perfect classifier, doesn't do any errors whatsoever. The random guessing has an AUC of 1/2, and anything in between is better than random, and the AUC tells me how much better it is than random. Now the AUC has a statistical interpretation which makes it very attractive, which you can look up in the slides how it's obtained. The AUC tells you the probability for correct order of random pairs with respect to the discriminative function. If you have a direction, like the perceptron vector, and class 1 is up there, class 0 is down here, and now you select randomly one data point from class 0 and one data point from class 1, the AUC tells you what is the probability that the class 1 example is further up than the class 0 example. So it has an immediate statistical interpretation which makes it very attractive. Okay, the AUC of the ROP curve can be used as a quality measure for comparing different classifiers, obviously. You can take it to your medical data analyst or whatever, the user of your classifier in the end, and then he or she can decide where do I want to put the working point. How important is for me to have a low false positive rate versus have a high true positive rate. There are competing schemes like precision recall, which are also useful and preferred in some other contexts, but they lack the simple statistical interpretation. Okay. For a multi-class problem, this is difficult to generalize. You would go to the full confusion matrix, and then people have come up with one number quality measures that are computed from the confusion matrix, and there's a zoo of different options. Okay. Accuracy is not enough, number 2. A machine learning urban legend. In the US military, it's always nice to make fun of military, especially the US military. In the 90s, they wanted to classify images of Russian tanks versus images from American tanks. They trained on a data set of photos, and they found nearly perfect classification in the training and also in the validation. But then the system failed completely in practice. I'm a bit scared about thinking what practice means in that example, but it failed completely. And then somebody looked at the data set, and the reason for this was that all the American tanks were photographed somewhere in Kansas, whereas all the Russian tanks were standing in the snow in Siberia, and the system had learned to detect the snow versus the green fields of Kansas, not the tanks, right? Now this is an urban legend, and as any urban legend, it is not true. At least not really true. But things like that happen all the time. And that's why you should avoid the blind application of machine learning in the sense of a black box, because you need to know what your machine learning system does. The system should be transparent, interpretable, ideally a white box, whatever that means, right? So we should know what the decision criteria the classifier, which decision criteria the classifier uses, and which, for instance, are the most important features contributing to the decision. And that we need in order to avoid artifacts, for instance, due to biases in the data set. We also get better insight into the problem, as I discussed it in the context of relevance learning, and we might potentially understand the underlying mechanisms behind the classification scheme that we're learning. One suitable framework is prototype-based methods, but that's not the only one. People are currently working hard on understanding, making deep learning more transparent in the sense that you understand what is going on, which filters are used, and so forth. The support vector machine is a bit better interpretable in the sense that you have a direction in feature space that you can interpret, things like that. But you should look into your classifier to understand what's happening. I have no idea. Okay, I'll skip that. I only wanted to say that sometimes accuracy is not even at all the goal of the exercise. All you want to get is some insight. And you might have some very small data set that still provides you with some insight without giving you brilliant performance of your classifier. And also that can be very useful. So don't hunt for good accuracies only, right? I have to skip that, unfortunately. Oops. And I have to skip that. You can read your way through that. I have to skip regularization, but I'll come to my concluding remarks, which is like 2 or 3 minutes, I hope. Dalia said, machine learning is just a tool. And I agree to a large extent. I would go even further and say it's not even a tool. Machine learning is a framework. It offers a variety of methods and concepts. And the difficulty is, first of all, to pick the right tool from that concept and then use it correctly. So it's not like a ready-made thing that you can throw at your data, or you throw the data at it and you get the answer. Normally it's not. If you think of classification, already in this school you have seen so many different schemes that you can use. K-nearest neighbor, LVQ, supervised self-organizing map. You haven't seen that, but it exists. Discriminant analysis, logistic regression, perceptron, support vector machine, blah, 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 blah. There are so many different schemes. Forests of trees, decision trees. And the same is true for regression, for clustering, for dimension reduction, for novelty detection, for reinforcement learning, which we didn't discuss at all here. So in the zoo, it's a zoo, right? In the zoo, think first. As a German comedian said recently, thinking, you know what that is? It's like Google, but it's inside the brain. I like that a lot. So think first. What is the goal? Is it only performance? Do I want to distinguish cats from dogs with 100% accuracy? Okay, fine. That's a valid goal. But maybe I want to obtain deeper insight into the data. I want to understand underlying mechanism. Is it realistic to apply machine learning to this? If you have 5 samples of 20,000 gene expressions, can you infer anything from that? Probably not. Right? Machine learning is not miracles. Consult the literature. Many people have done many things before you started even thinking about this. Right? Inspect the data. Think about how to represent the data, how to normalize, or whether you want to normalize, about transformations. Do unsupervised analysis in terms of correlations. Do PCA. PCA first is one of my statements. Are there any clusters? Is there a structure that I can recognize from the data? Can I employ visualization techniques to see something, to understand something about the data? And start simple. So this is the last slide that I started with. Start simple. Use simple classifiers first. Increase the sophistication of the system to get deeper into it. And accuracy is not enough. I just told you about that. Some challenges in practice: imbalanced data, incomplete data, noisy data, functional data, privileged information, heterogeneous mixed data, non-vectorial data, transfer learning, lifelong learning, representation learning, interpretable models. There's an endless list of challenges that still await solution. Machine learning is not yet there. It's not ready. Maybe it never will. Here's a few textbooks that I would like to recommend, but that you can read on the slides, and that's pretty much it. This is not a random forest, it's a real forest. Okay. Yeah, thank you.
Anyone has questions?
Well, I will see you all in the tutorials, and I hope you have tons of questions, because otherwise I will be bored. Right?
So, thank you very much.
Thank you.